thank everybody for tuning in today on Monday. I'm going to be presenting a paper that was just published in Analytical Chemistry, and it's about our charge detection work. We've built a homemade instrument, and we've used it for Megadalton polymer characterization, which is why I got invited. But in truth, the paper is really an analytical paper describing our instrument, what we had to do to put it together, and then giving examples of the Megadalton polymer characterization. It's just a polyethylene glycol high molecular weight sample. And then in the second part, we've used the instrument to measure droplet dynamics spraying from methanol solutions. And I'm going to discuss some different aspects of charge detection mass spectrometry. And it's going to be particularly useful for polymer characterization, just because it's capable of measuring such high masses and high mass to charge ions. And one of the challenges for us is finding methods to accurately calibrate the instrument, and that was a kind of a central focus in the paper that just came out. Okay, so I'm going to start with just describing some general characteristics of charge detection, and it's touted for enabling access to extremely high mass macro ions, okay, beyond the Megadalton regime. And in charge detection mass spectrometry, you're really doing detection of individual ions, individual particles. And when you're measuring one particle, you're going to have directly a measurement of that particle's charge. And then at the same time, you're going to measure the mass to charge of that same particle, determined from its velocity through the charge detector device. So it is a non-destructive analysis, enabling the possibility to perform other types of experiments upon exiting the charge detector. And one disadvantage is that there's a kind of a high minimum charge threshold for detection of species. And often it's several hundreds of charges. And then even with our kind of low noise circuitry, our particular instrument, we evaluated the instrument limit of detection at about 510 charges. So as you can tell, we really need to be able to charge up species in order to see them. If we can't put 500 charges on a particle, we're going to have difficulty seeing it. Okay, so in terms of what makes charge detectors interesting are some of the potential applications. As I mentioned, we have access to very high mass ions, including polymers. So that's why I'm here today. There's also a lot of interest in biological applications, looking at high mass species like viruses, that you can't really see easily on a conventional mass spectrometer. Organelles, also supramolecular protein complexes, whole strand DNA, and nanoparticles. Well, the Gerald group at Indiana and also Evan Williams at Berkeley are really a couple of the leading groups in advancing charge detection mass spectrometry. And they've gotten good support to build great instruments. we started off with a very modest support, and our instrument was really based upon kind of reconfiguring a vintage triple quadrupole. Okay, this was a Quattro 1 originally manufactured by Micromass, now Waters. And basically what we did was we took an old triple quadrupole and we removed the back quadrupole and the collision cell. And it's in this region here that we placed our charge detector. All right, so we've got a photo of the instrument here, triple quadrupole, and then this view here is looking straight down. There's kind of a window there into what was the triple quadrupole, and what you see, well, what's not shown here is a Z spray source, Z spray from Micromass, and then we have the original first quadrupole and the charge detector installed behind it. So essentially, our charge detector is just a tube, a metal tube, and in the functioning of a charge detector, you have an ion that enters within the tube. Okay, we've surrounded our charge detector tube with a second really grounded shielding tube to cut down on noise. But we have an amplifier here that is going to sense this highly charged particle as it enters our tube, okay, made out of stainless steel. All right, so as I mentioned, we've got a highly charged particle here, more than 500 charges as it enters the tube. And then, so what happens is, as this highly charged particle enters our tube, we have electrons that are attracted to the surface of the tube. So that creates this spike related to this movement of electrons toward the edges of the charge detector tube. Once the particle is inside, things kind of stabilize, and we're in this region here of really little movement stability. Okay, but when the charged particle exits the tube, then we have the electrons that had been detected to the charge detector walls, they go back to their original points, and that there's electron movement generating a current, but this time in the opposite direction as things go back to the original condition. All right, and then, so essentially in our experiment, we're going to be measuring two things. We're going to be measuring the magnitude of the charge, which is really proportional to the area of the spike. And the two spikes, of course, should be symmetric. Okay, so the area, or sometimes the peak height, is used, and that's going to be proportional to charge. With the calibration, that's going to give us our charge measurement on this single particle. The second thing we're measuring is actually the residence time inside the tube. And that is really the time between our initial spike here and our exit spike. So that time, residence in the tube, and I'll show it as time of flight on later slides, that is going to give us information about our mass to charge value. So we have that combination of a mass to charge value derived from the residence time inside the tube, plus the magnitude of the charge given to us by really the integral of the peak area, or sometimes it's the peak height that's used. So I'm going to switch over now, and I'll show you kind of a schematic diagram of the circuitry that we use in the charge detector. Okay, so here's our charge detector tube. And of course, all this is housed under vacuum here. Our charge amplifier, of course, is under vacuum, and we have a detail of the circuitry shown here. So the key points are our JFET right here, okay, and I'm just going to scroll down here to our experimental section. So this is a N-channel junction field effect transistor, JFET, okay, and it's characterized by low input current and low noise, and then it's followed by a high-speed, low noise, low power draw bipolar operating amplifier. Okay, and so that's shown actually right here. That's U2, the operating amplifier. Okay, now our design is really based upon the first to know Benner design of quite a few years ago. So afterwards, then outside the vacuum chamber, then we have a series of filters and an oscilloscope and a PC for capturing our different particle events. Okay, so in order to consider that we've gotten a decent signal, a usable signal, what we're really looking for is a signal that has this type of shape. Okay, so it's non-ideal compared to the ideal signal that I showed you on the previous slide. And actually, the real data is often, a little bit noisy, as shown by the blue line here. That's the blue curve is the real data. Okay, but we have our data system. What it's really looking for is a symmetrical input and output pulse. Okay, and if it sees that, then it's going to say, okay, I've got a real event, a real entering and exiting of a particle inside the charge detector. And then what it's going to do is create a kind of idealized curve corresponding to that event, that detection event. Okay, so for a kind of a noisy real signal event, we're going to fit that event with the type of curve that you see in red there, and that's going to be our signal. And it's really from this fitted curve that we're going to extract our amplitude, and again, that corresponds to the charge of the particle, and then our width, which is going to correspond to the residence time in the charge detector. That's going to give us our mass to charge information. I'm going to go ahead and I'm going to attack the polymer data.
Sorry. Let me ask one question.
Okay, sure.
What you're showing is just a single charged particle passing through, but
Right.
I'm sure you're getting multiple particles at the same time. So
Right.
what does the signal actually look like for a real experiment?
Okay. Well, we have, this is a really short time scale there. This is a microsecond time scale. We're capable of seeing something like 200 events per second. Okay, now, if it turned out that multiple particles entered at the same time, then it would kind of give a confusing type of signal. So the data system would reject that. It's only when you have like this clean input and exit signal that a data point is registered. But you're absolutely
thank you then. Yeah.
You're absolutely right that you could have multiple events occurring, but the data system is going to reject that. Okay, and just another point of clarity, this system, it's just a one-pass system. There's other systems where you send the same particle back and forth through the charge detector, making multiple measurements on a single particle. Our system is a so-called single-pass system. Okay, so okay, what you're looking at here is a so-called density map of our 2 Megadalton polymer polyethylene glycol. So, so what we've done here is we're really looking for the peak signal here because that's going to give us something reproducible that we can try to get a good mass measurement on. But you can see that this kind of composite signal, which encompasses thousands of events, gives us a kind of an indication that most the peak signal occurs for this particular time of flight, that's residence time, if you like, inside the charge detector. Okay, and you know, our challenge though is we need to be able to, of course, convert our time of flight scale here, residence time in the charge detector, to a mass to charge scale. Okay, that and in general, time of flight here scales in the same direction as mass to charge. So species that take a longer time of flight are going to be of higher mass to charge values. The species that exit more quickly to the left, those are going to be lower mass to charge species. All right, and I'll mention that a group like the Gerald group at Indiana, they have a very sophisticated device where they've put a type of electric sector that's an energy filter before their charge detector. So they have very clear, precise control of the energy of all the particles that they're measuring. Okay, I wish that was the case for us, but it's not. This is, as you saw, a home-built instrument, a lower cost instrument. Okay, that's its big advantage. But we don't have some of the advantages in terms of being able to know the initial energy of our particles. And that's going to cause difficulties when it comes time to convert and calculate our mass to charge values. Okay, and so I'll show you our second, just this second portion. It's exactly the same spraying solution of polyethylene glycol. Okay, but this time we have increased the acceleration of our species. And so when we increase the acceleration of our species, then you can see that the peak value shifts to lower residence time inside our tube. Okay, that makes sense. We're accelerating these ions to a higher value. Of course, they're going to move through the tube more quickly. Okay, so this gives you an idea here of a type of presentation, density map showing the distribution of different oligomers, okay, each measured as individual particles as they pass through the charge detector. All right, so now,
Richard,
yes.
may I ask a question here now? Like, do you define a kind of resolution with this CDMS technique? And if you do so, does the length of your charge detector cell have an impact on this resolution? like as a time of flight, like the longer the tube, the better the accuracy of your measurement? Do you have the same kind of effect here? If you had a very long cell, you would have a better accuracy in the measurement of the time of flight and then in the M over Z, or not really?
Yeah. Yes, but there's many factors that go into determining the quality of your measurement. And I'm actually, we did quite a bit of work on characterizing the error in our analysis. So I'm going to discuss those.
Thank you very much, sorry.
But I'll just say there's a lot of factors that go into it. Okay. But I'll say from the outset, if we had a beam of uniform energy, okay, if we had like a type of electric sector before the charge detector, then that's going to simplify things and improve your analysis quite a bit. Okay, so in some ways, we have some, we have a lower cost instrument here. That's its advantage, but we have some disadvantages in terms of our data treatment, and I'm absolutely not going to hide those. I'm going to discuss those in detail. All right, so I'll have to do a little bit of mathematics here, though, to explain how it is that we obtain our mass to charge values. Okay, so for our charge detector, our mass to charge, here I have Q as charge here. Okay, but our mass to charge value, it's of course the inverse of Q over M as shown here. Okay, but how do we get at it? Well, it turns out that the square of our measured velocity, okay, so this is what we're measuring, is equal to the square of the initial velocity plus 2 times our acceleration voltage, okay, times the inverse of mass to charge. Okay, so we're doing our measurement here. We have that value. We can accelerate to a very precise value. How do we do our acceleration? We just put a bias voltage directly on the charge detector itself. So we can very accurately accelerate ions into the charge detector. Okay, and we can have a very accurate difference in acceleration values. Okay, what we are really bad at is evaluating the initial velocity. And think about it. Okay, here we have a modified triple quadrupole with a so-called Z spray source. So we're doing electrospray way back, under atmospheric pressure. Then we have 2 regions of differential pumping, and then finally our analyzer region, which is at about something like 10 to the minus 5th millibar or so, maybe a little bit lower. Okay, so what determines our initial velocity here? Well, it's really that vacuum that's pulling ions into the mass spectrometer. Plus, we have a series of electrostatic lenses on the inside of the mass spectrometer. So really, it's actually quite complicated to know what that initial velocity is as your ions head into the mass spectrometer. And in addition, imagine you change some pumps because something breaks down. Then, your pumping condition just had changed slightly. That could have an effect on the initial velocity. Okay, so this is a real difficulty for us to evaluate accurately. Okay, but fortunately, there's a little mathematical trick whereby if you do, in fact, 2 measurements, but at different accelerating voltages. Okay, so here we have 1 accelerating voltage, D1. Okay, we repeat the experiment with the same sample at a different accelerating voltage, D2. then we can rearrange these equations to solve for mass to charge. And the very fortunate thing is that the initial velocity drops out of the equation. So we can solve for mass to charge values as twice the difference between our accelerating potentials divided by the squares of the two measured time of flights through the charge detector. Okay, so this really is what enables us to calculate mass to charge values without having to worry about the initial velocity. It drops out of the equation. All right, so that's how we're going to evaluate mass to charge values in our experiments. All right, so what we did then is we're not just going to rely on two measurements. Here, what I've done is I've looked at that peak value of our 2 Megadalton PEG polymer and measure its or measure what velocity corresponds to the peak value, okay, for that PEG polymer mixture at various acceleration voltages. Okay, so basically in this plot, what we're doing here is we're considering this to be the equation of a line, and we want to put it in a kind of a y equals mx plus b form, and our y is the measured velocity squared. That's our y-axis over here. And then our x-axis is minus the accelerating voltage, minus UD here. Okay, so what's that going to do for us? Well, from this plot then, okay, the slope is going to be equal to this 2 times Q over M here. So from the slope, we're going to be able to evaluate mass to charge, and even this V naught squared is going to be our intercept. Okay, so we can even evaluate our initial velocity from this plot. All right, so you can see that we have a good linear plot based on 4 points at 10, 20, 30, and 60 volts acceleration. Okay, but we have a little problem at 0 volts acceleration, and really, what's that due to? Well, it turns out that if we put a negative bias on our charge detector, then like say minus 60 volts, then we're very efficient at pulling cations into the charge detector. We can see that this is showing counts over a certain time as a function of the acceleration voltage, the negative voltage placed on the charge detector. Okay, so we're still pretty good down at 30 and okay at 20, but okay, and even 10, but by the time we get down to 0, we're having trouble pulling ions in, so we have a low count. So we really think that explains why our point at 0 volt is no good. It's just a kind of, we have very poor statistics coming in there. Okay, so again, these points correspond to that peak value. And from this plot, an analysis of the slope gives us a mass to charge value for our peak of approximately 5,930. Okay, and then in addition, as I mentioned, we can do an extrapolation to nu naught here, our initial velocity, and we calculate that as 805 meters per second. That gives you an idea of how fast things are being pulled into the mass spectrometer. Okay, that's 805 meters. That's almost the length of a football field per second. Not quite. All right.
Richard,
so, Yes, go ahead.
I'm sorry. Do you have actually a way to compare this value with a whatever a manufacturer, like a vendor, can tell you? Like, does this number, like, of initial velocity make sense? Like, is it okay, or like it's and like, I'm sorry. Do you have a way to measure that, or like ask vendors to tell you if this number makes sense? This 800 meter per second.
Oh, I thought you were talking about the polymer values.
No,
Okay.
I mean yeah, like the V0 value. I don't realize actually how fast my ions are moving in my mass spec. Like, does this value make sense to you? I'm really ignorant on that value. I don't know.
Yeah. Well, as I mentioned, that value, it's hard to measure, and
okay.
So I stand by our measurement, though. But I don't have I don't have anything really that I can point you to compare that with today.
Okay. No
All right.
No problem.
So no problem. Okay. So now, so now we're going to go to the analysis of our polymer, and again, this is based on several thousands of measurements. Okay, and so basically, we see our mass to charge distribution over here on the left, and let's see. So this value is going to peak at about 5,930. Okay, but you remember that I mentioned to you earlier that we have difficulty measuring species that have less than 500 charges. Okay, so if we take a look at the charge distribution of the different species that we detected, you see it's kind of peaking, well, somewhere around 700 charges or so, roughly. Okay, but what you need to keep in mind is that, you know, below about 500 charges here, we're having trouble distinguishing signals from the noise. Okay, so we have an inherent bias against measuring species at the low end here, notably below about 500 charges. All right, and so then, of course, if we have a mass to charge distribution and a charge distribution, we just have to multiply those two together to obtain our mass distribution. Okay, and that's shown here. I'd say the average mass is about 7,000 or so. Although you know, our peak is not symmetric, so we're peaking at closer to 6,000 Megadalton. All right, and so it's clear that these last two values are really biased against the lowest charge species. Okay, so the true distribution really includes more species at the low end. It's just that we can't detect them efficiently. Okay, so then what about our mass distribution? Well, clearly the lowest mass species are going to be those of lowest mass to charge. So that means also here we are biased against the lowest mass species. All right, and I'll say that our value from the last figure there, 4C, gives us a peak mass of approximately 4.45 megadalton, and this is higher than a previously determined value, also in the literature, of 2.7 megadaltons. Okay, and with that other system, they were slightly better than us at measuring lower mass species. So that can kind of account for the difference there. Okay, I'm going to stop there. Any questions about the polymer characterization aspect of our instrument and the example here?
Yeah, I do have a quick question, if you don't mind. I was wondering if you would have any way to kind of activate this big polymers, like to make them fragmenting, to get like at the same time like the molecular weight of this large chunks of polymers and a bit of information about the nature. Do you know how much energy you would have to bring to these big things to make them fragmenting, like dissociating into fragments to see the typical PO fragmentation pattern? Would that be possible?
Well, I'd say that since we have a non-destructive analysis, then it is possible to do further experiments as species exit the tube. Okay, but our instrument is not yet set up to do that. I'll put it that way.
Yeah, sure.
Just out of curiosity, is there any way to overcome that 500 charge limitation, or not presently?
Well, yeah, it would be to improve, to improve the shielding on our instrument and go to even lower noise components. It's really electronic noise that we're up against.
Okay, the reason why I ask is because this seems like just an amazing application. Have you ever thought of looking at quantum dots? Because now this could be something ideal if you wanted to get into the electronics materials industry for helping, ensure the reproducibility of batch to batch. Even if you don't have the exact molecular weight, if you could show, oh, this is reproducible, this one's out, I think this could be a huge improvement for them.
Okay, I'll keep that in mind. Thank you for that.
You're welcome.
Okay, so since we're talking about that noise evaluation, I just want to really give you some more detail on that right here. And what we've got here is a means of estimating our electronic noise in our system, which really is pretty constant electronic noise. And how we measured it is we're giving repeated voltage pulses and just doing repeated measurements on a signal that corresponds to 3,121 charges. Okay, so these little spikes that you see here, those are all signals corresponding to about a little bit more than 3,000 charges, which appear on top of this noise level here. You can see the noise level. And so, that gives you just a little bit of an indication of how easy it is to see something with 3,000 charges. Now, if you have a signal that's 1/6 of that, that's our 500 charge zone. You can imagine that 1/6 of this signal is going to give us difficulty at being sure that we're detecting something. Okay, so we have, from this measurement, we've been able to assign root mean square noise value of about 170 electrons to our system. Okay, so where did I get this 500 minimum charge number? It's just merely 3 times the RMS noise. 3 times 170, our noise level, equals 510 charges. Okay, so that's really what defines our instrumental limit of detection. Now, just one other little point is that as we change the mass, as we change the charge level that we're measuring, this noise level, it's really detector noise. It stays constant. So what that means is that, as we as we go up in the number of charges, for example, say we went to 170,000 charges, okay, then our signal to noise would be 1,000. 170,000 charges divided by 170 RMS noise. It would give us a signal to noise value of 1,000. Okay, so the point is, as we go up in charge, then our signal to noise quality keeps improving. All right, so for the final portion of the talk today, I'm going to be looking at charged droplets of methanol. So we're going to be spraying pure methanol and trying to get some measurements of droplet dynamics of massively charged methanol droplets. Okay, so for these experiments, we turn down the heating of the source. So it's the source temperature is just at room temperature now. And this is going to enable us to generate huge, huge droplets that we're going to measure with our charge detector. Okay, and so here we're looking at a few signals that were acquired here by the charge detector. And so what you notice is, okay, these signals, of course, occur as paired peaks. First, we have our negative peak, then the positive peak. Okay, and we have two others that are observed within this time frame. Now there were some smaller peaks, that means lower charge species. Okay, but we couldn't identify matching exit signals for those, so those were not counted. Okay, but basically, if we take, for example, this first signal that was detected and then zoom in on it, you can see that we had, with this massively charged methanol droplet, we have very symmetric entrance and exit signals. That allows us to get a high signal to noise measurement of charge as well as residence time inside the charge detector. Of course, that leads us to our master charge information. Okay, so then here we have a so-called scatter plot, and this is thousands of points here in repeated measurement, looking at charge versus residence time, time of flight in our charge detector. Each dot corresponds to a single signal that was measured of a highly charged methanol droplet. And you can see here that we're measuring species up to, this is one droplet that holds 30,000 charges. All right, and each point represents an individual droplet measurement. Okay, so we thought, oh, we've got like a lot of activity, like here, this is the density map. We got a lot of activity down here, okay? But what was also kind of quickly visible and caused some immediate questions is, wow, it seems like we have a real stark border here. And so in this so-called scatter plot, we thought about it and we said, oh, well, let's consider that we're on this, that we're only looking at charged particles that have 10,000 charges here. Okay, and I told you earlier that this time of flight scale here, our x-axis, corresponds directly, or I'll just say it tracks in the same direction as mass to charge value. So if we're way out here, looking at this horizontal line, only species that have 10,000 charges, we're looking at really high mass to charge value droplets. Okay, as we move to the left, what's happening is that we're getting the droplet, its mass to charge value is decreasing, but its charge value is holding constant. So that means we're looking at smaller and smaller droplets. that all hold exactly 10,000 charges. But if we keep going, we reach a point here, a certain droplet size, beyond which we see nothing. Okay, and we realize that this stark border here corresponds to the so-called Rayleigh limit of charging. That means a droplet now with 10,000 charges has gotten so small that if we go any smaller, there's going to be a so-called Coulomb fission event, a droplet explosion. Okay, so really, what we've got now is a visual indication of the Rayleigh limit of charging here. Okay, and it corresponds to this line of points. And so, well, I'm going to take you back here to the Rayleigh equation. Okay, and just as a reminder, okay, this Rayleigh limit, the Rayleigh equation was first given way back, I think 1882, by Lord Rayleigh. It says that the maximum number of charges that you can get on a droplet is going to be proportional to the radius raised to the 3/2. Okay, our sigma value is surface tension. We have the permittivity of the vacuum. That's our epsilon naught and constant 8 pi. Okay, so basically, what we notice here is that we've got a bunch of constants here. Okay, and for pure methanol, sigma is going to be simply the surface tension of methanol. Okay, but our charge is going to be directly proportional to the radius of our droplets to the 3/2. Okay, so what we decided to do was some more measurements and to see if we could really prove that these points were at the Rayleigh limit. Okay, so here I've got another scatter plot. What we're doing here is we're accelerating these droplets to different values, and we've changed our acceleration method here a little bit, and we're using the cone voltage setting on our electrospray source to increase the acceleration. Okay, what we had to do that because we have only a limited range whereby we could change the bias on our charge detector, as I showed you previously. Okay, so here we're accelerating by changing the cone voltage. Okay, so we decided to try to find out, does that give us the intended shift that we would be expecting if we had droplets at the Rayleigh limit? Okay, so what did we do? First we drew an empirical line. This red line, it's a straight line, empirically drawn at really right at the limit that we're presuming, we're testing to see whether it's at the Rayleigh limit. Okay, then we have certain ions, particles that we've detected at the Rayleigh limit, and we can calculate if indeed those species are at the Rayleigh limit, where they should be shifted to when we accelerate to 150 volts and then 300 volts. Okay, so the red lines here indicate the expected residence time in our charge detector if indeed these droplets are at the Rayleigh limit. And you can see that there's a decent correlation there. Okay, so then we took this one step further, and we have to do two things. We presume we're at the Rayleigh limit, and we have to presume that our droplets are spherical. Okay, so then we can use those species at the Rayleigh limit to calculate, to calibrate is what I wanted to say, to calibrate our mass spectrometer. Okay, and so Okay, why can we do that? Because we know that at a certain value of charge, that species at the Rayleigh limit has a certain radius to the 3/2 value, okay? And for a spherical droplet, from that radius to the 3/2 value, we can calculate the volume and then the mass, okay? So that's how we can obtain our mass, okay? At this limit here with known charge. Okay, so from that, we obtain our droplets dynamics plots that I'm showing you on the bottom. Okay, and actually, we took values, we had to move to a slightly more dense region. Okay, so we're slightly below the Rayleigh limit here, but still within 80 to 95% of the Rayleigh limit to calculate these values here. And you can see that the size of the droplets we're measuring, it's between, say, 10 and 20 megadalton, okay? And these correspond to charge values around 6,000 charges and droplet radii of about 200 nanometers, okay? So these scales here are not linear, okay, all of them, but if we're truly at the Rayleigh limit, then all these values are valid. Okay, so that's how we were able to generate these plots. Okay, so now the final thing I want to present today is more proof and evaluation of really how close we are to the Rayleigh limit. Okay, so we did this plot here of this is using the Rayleigh equation. If we plot z squared versus mass, if indeed we are truly at the Rayleigh limit and looking at particles that behave exactly according to the Rayleigh equation, then we should have a linear relationship between charge squared and mass. And you can see it's pretty good. It's not perfect, but it's pretty good. All right, and then we went back then and we looked very closely now. You know, I think you can agree that the anticipated movement of our red lines here, which correspond to expected behavior if we're truly at the Rayleigh limit, I think you can agree it's pretty good. But if you really look closely, the shift is a little bit more than it should be, okay? In other words, in each case, especially here at 300 volts acceleration, there are a few points to the left of ideal behavior, okay? And there's two possible explanations for actually what it is an increased acceleration of these droplets relative to what one would expect at the Rayleigh limit. Okay, the first explanation is that in fact, we're accelerating these droplets to higher values than is indicated, okay, by our change in cone voltage. All right, so for me, that seems less likely than our second explanation, which is that in fact, the droplets which are to the left of the red line are actually charged to levels beyond, above and beyond the Rayleigh limit. Okay, and there's been some work done by the Beecham group quite a few years ago that showed that actually methanol, pure methanol droplets like we're showing here, can charge up to about 120% of the Rayleigh limit. Okay, so if that was indeed the case, those species charged beyond the Rayleigh limit, okay, a higher level of charging than anticipated, would be accelerated more than anticipated. And we really think that that is the best explanation for these values that appear to the left of our red line. So we did a little bit of error analysis on that, and we found that, in fact, in our worst case, we're at about 12.3% above the values that we're anticipating if they were truly at the Rayleigh limit. We did this by a one-sided distribution analysis, okay, only looking at the species that were more highly charged than anticipated. Okay, so if we have an error of about 12% here, I mean, that kind of gives you an indication of using this method as a calibration method, okay? And just to remind you, Beecham and co-workers showed that the actual charging was actually about 120% of the Rayleigh limit. So it turns out, you know, we're in a zone whereby the actual charging level of those droplets compared to that predicted by the Rayleigh equation might be giving more of an error than the mass to charge value measured in our instrument. So we have assembled and installed inside the vacuum chamber of an old triple quadrupole, a charge detector equipped with low noise charge amplifier. It has a complete electronics system that we designed and assembled based on the Furstenau and Benner design. We enabled communication with the data acquisition system, installed analog and digital filters, tested and calibrated the system, and created a set of scripts for data analysis. Okay, so our instrument has a limit of detection based upon 3 times our RMS electronic noise of about our instrumental limit of detection, about 510 charges. We can detect about 200 events per second. We showed the distribution of our Megadalton polymer, PEG, centered, well, with a kind of a little bit of an asymmetric peak, around 7,000, 6,000 to 7,000, with the peak population near about 4.45 megadalton. For our droplet experiments, we showed that the highest population of methanol carries about 5,000 to 7,000 charges. Most detected methanol droplets near the Rayleigh limit were in the range of about 10 to 20 gigadaltons, but we had some at the very high end extending up to 70 gigadaltons. So really high mass analysis. Okay, we did quite a bit of evaluation of both error in charge, measured charge, and also measured mass to charge. And we showed that the maximum error of our method calculated to be about 12.3%. Okay, but the uncertainty in the true level of charging away from the Rayleigh limit is likely to be even greater. And then lastly, you know, if you have an instrument where you don't have a direct measurement of your ion energy, we think that this method, visualization of the Rayleigh limit, is going to find value as a way of verifying mass to charge values, a kind of a calibration aid, okay, for those mass spectrometers that don't have a way of defining ion energy. Okay, thanks very much for your attention. Appreciate it.